Let's look at another example from section 10.7, where we will this time utilize that work kinetic energy theorem. Here we have a solid disk with mass 2 kilograms and radius 30 centimeters that has a half kilogram block suspended over one side with a string. Now that suspended block will start from rest and then descend to a position 1 meter lower. The question is, what is its speed when it gets to that point? Like I said, we are going to use the work energy theorem to consider this particular problem, where again we could say that the work is going into the change in the kinetic energy of the block. Now the work here would be work done by gravity. We know that gravity is going to be pulling on this block with a force from its weight over this displacement, or this delta y. So if we were to take work as a force, or mg, times a displacement, where that displacement is that change in the height of the object, there's the amount of work done by gravity on the system. Now that work done by gravity is going into changing the kinetic energy of the system. What we need to recognize here is that this system is going to involve two types of kinetic energy. We have the 1/2 mv squared of the block itself, a translational kinetic energy of this block simply moving in a downward direction. But we also have the kinetic energy of rotation. This wheel is now going to begin to spin and rotate. So we also have a 1/2 I omega squared as an energy that is also present. So what we're going to do is simplify this a little bit, because right now we have variables that just aren't matching up. We have a v in this piece of the equation, which we want. We're looking for a speed at the bottom of this block's descent. But here we have i's and omegas that aren't matching up. So we are going to replace those variables. For the I, we're going to replace it with the moment of inertia of a solid disk or cylinder, which is 1/2 mr squared. For the omega, we want to write this in terms of v, so that we have a v here and a v in the other piece of the equation as well. Now, since we know that v is equal to r omega, then we can rewrite omega as a v over r. And that quantity is going to be squared, because it was omega squared. That means that we can actually cancel out these r's, because there's an r squared there and an r squared there. And we can simplify our expression a little bit, so that mg delta y is equal to 1/2 mv squared, plus this would now become a 1/4 m, capital M there, v squared. Take a second, plug in your variables, and see if you can solve this equation. Lowercase m was representing the half kilogram block hanging. G, of course, is 9.8. And the delta y was the 1 meter descent. Again, this lowercase m is the half kilogram hanging block, moving now at some sort of speed that it has gained. And the capital M is the larger 2 kilogram mass of the pulley or the disc itself. Pause the video and solve for v, and you will have the final velocity of this block. You should get about 2.56 meters per second. Check yourself and make sure that you got it too.